Hi everyone, let's start Module 4. In this section, we're going to look at optics, which is the study of light. The question, what is light, still doesn't have a simple answer, so I'm going to go over a brief history of some of the models of light. In 1660, Newton decided that light is a particle. There's always been this question of, is light a particle or a wave? And he concluded that light didn't show diffraction. Diffraction is a wave property. It's the bending of waves around an obstacle, or the spreading out of waves through an aperture. We know now that light does in fact show diffraction, but at the time it was thought that it didn't, and that light must be a particle. Then in 1801, Thomas Young showed interference of light, and interference is a wave property. So I've drawn some interference fringes here, we know what interference is from discussing waves on a string and sound waves. It can also happen with light. So if you imagine taking a piece of paper, I have one here, and then cutting a slit down the middle or a hole there, if you were to hold it up against the wall like this, and then spray a can of spray paint on that line, when you removed it, you would just see one line where this is. You would see a stripe where the paint passed through the paper. So instead, if you were to have a screen here and you could do this experiment with light, you would see interference fringes, which are periods of constructive interference. And we'll look at that further when we look at light as a wave in Module 6. But for now, since light did exhibit interference, which is clearly a wave property, it was decided that light is a wave, and it must be an electromagnetic wave, which is produced by oscillating electric and magnetic fields. So, however, light does also show some particle characteristics, mainly in how it interacts with matter. And we'll also talk about that later, specifically the photoelectric effect and Compton scatter. So in the early 1900s, Einstein proposed that light is a photon, which is a model that considers both wave and particle characteristics. So the nature of light is actually not distinct. Light behaves as a wave in some scenarios, and it behaves as a particle in others. And this is called wave-particle duality. So again, we're going to come back to that in modern physics. But for now, let's look at a few models of light that can be used to model different phenomena. Okay, the three main models of light are the wave model, the ray model, and the photon model. As I was saying, the wave model assumes that light is a wave and it's an electromagnetic wave. So let's recall that electromagnetic waves do not require a medium to propagate. They can travel through a vacuum. And in a vacuum, electromagnetic waves will travel at the speed of light c, which is 3 × 10⁸ meters per second. And the wave speed equation, v = lambda_f, still applies. So if it's an electromagnetic wave, we know that the wave speed would be c = lambda_f, where lambda is the wavelength and f is the frequency of the light. And we'll use this again later on in this module. Okay, second is the ray model. The ray model assumes that light travels in straight lines called rays. And this model is really useful in geometric optics, so we're going to focus on that in a second. The third model is the photon model, which says that light consists of photons. Light is quantized into small packets of energy called photons. And these photons have both wave and particle quantities. So this one explains really well the interaction of light with matter and quantum theory of light. Okay, let's look further into the ray model. If we consider a light source, then light will spread out from that source in all directions in spherical wavefronts. Wavefronts are technically points on the wave where all points are at the same phase. We can imagine light rays. Light rays are straight lines that are perpendicular to wavefronts and show the direction of travel of the light energy, or the direction of propagation of the wave. And they're always in straight lines. So in general, the ray model is an accurate model or a good approximation for these systems, as long as the aperture that the light passes through is much larger than the wavelength of light. So as long as that's much greater than about 1 millimeter. And this is almost always true for lenses and mirrors, so that's why this works really well for geometric optics. All right, I just want to go over a few more points about light rays and then some definitions. So light rays travel in straight lines. They cross without interacting. They'll travel forever unless they're blocked and they interact with matter, so they can reflect, refract, scatter, or be absorbed. And objects are sources of light rays, and the eye can see by focusing a bundle of light rays. So they're going to be very useful in this section. All right, so as I said, objects are a source of light rays, and they can either be self-luminous, meaning that they produce light, like a light bulb or the sun, or reflective. And any other object that we see is reflective. So it's reflecting light, that's why we can't see if there's no light at all. So we need light reflected off those objects, which will then enter our eyes, and we can see it. In general, objects will emit light in all directions unless blocked, as I was saying. So there's further two types of objects, or two types of light sources, which are point sources or extended sources. So point sources, just a single point that emits light, and then we can imagine that extended sources are made up of many point sources. The last type is a parallel ray source. A laser is an example of a parallel ray source. So for an object or a point or extended source, when you're looking at that object, it will emit light in all directions. So we can be standing many different locations and we can see that object as long as light enters our eyes, meaning that it's not blocked by something else. However, with a parallel ray source, we would have to position our eye so that light enters our eye so that we can see it. And if you think about a laser, you can only see that laser, the light from the laser, if it's directed right in your eye, which isn't a good idea, or if it's reflected off of something else. And I would show you that if we were in class. I'm kind of disappointed we can't do this section in class because I do have a lot of great demos, but I'll try to find some videos as we go, maybe make do. I should have ordered a laser. Anyway, okay, so another example of a parallel ray source is a very distant object. If we look outside at a tree, something that's fairly distant, the light rays it emits are essentially parallel. And we'll use that concept as we go on to look at mirrors and lenses.